Hello everyone, so it's part 3 of the video. The last video finished off on you having to attempt the 6 marker. This is the next question, question 3, which is looking at energy profiles again and with some bond energy calculations. The bond energy calculation is higher, just so you're aware. So this question is about reaction between hydrogen sulfide and oxygen. The equation for this reaction is 2H2S, and it's gas, it's gaseous. You got 3O2, which is also gaseous, to change to hydrogen, water, and sulfur dioxide, which are all in gaseous form. And we know that from the state symbol. Right. So the beginning of our reactions, so this bit's our reactants, the arrow, and then to our products. And this will lead us nicely onto our next question. So what does H2OG represent? So we've got the G and it's water. The only thing it could represent, so it's not solid. If it's solid, it'll be ice. Just let it focus for a second. So if it was solid, it'll be ice. If it was liquid, it's just water. But in gaseous form, it has to be water vapor. Water vapor. Now we're going to skip B for now. Look at question C. Now we have another energy diagram picture. Just like we saw earlier. And this one's got most of it labeled up, but it's missing the last part of the reaction. It says here specifically what you need to do. So figure 1 shows part of the reaction profile for the reaction. The reaction is exothermic. That's key. Doing red actually. Exothermic. You need to complete the energy profile line, label the activation energy, and label the overall energy change. So as I said before, if you do it all the time and keep labeling it, it should become second nature. Right, so beginning of our reaction, that we saw earlier, which I got here, in this page here, got on the screen. We had H2S and 3O2, which is our reactants, and then we've got our products here at the end. So first of all, because exothermic, we know that the products are going to be a lot lower down than our reactants. So we label it here our reactants, so we know this what we're starting from. Our products are going to be lower down because energy has been released. So I'll just draw it lower down somewhere, and then we write our products. Now, if you write the word products, you wouldn't get a mark in this case because the question's already given you the reactants here in terms of the reaction we saw on the question. So here you're not supposed to just write products, but it's good to label it products, but the answer isn't products. You actually have to write the symbols and the chemical formulae. So it's 2H2O, and this shows that you understand the difference between products and reactants. And then we put the G in as well to show that we know the state symbols. We complete the diagram by joining the rest of the energy profile to this part of the diagram. Now, we've completed the line. It's done. Label the activation energy. So we know the activation, the amount of energy required from the reactants to start the reaction. So that's from the peak here, this point. So if we start drawing a dotted line across, this is our activation energy. And then tick. Then it wants to label the overall energy change. Now that's just the energy for the entire reaction to take place. So if we just extrapolate backwards from this line here, now it doesn't have to be accurate, it wants you just to label it. So as long as we can represent that, and I'm going to have to draw an arrow down here to fit it on. Overall energy change. That's 3 marks, that's done. And now we complete the diagram. Now the next question, last question we're looking at together, is the bond energy calculation. And this one is a little bit trickier than ones we've seen before. But I wanted to show you other ways they might show you this question. And then my camera has decided to play up slightly. So we can. Right, so we appear to have camera back on. So this question, last question we're looking at, is D. Figure 2 shows the display formula equation for the reaction for hydrogen sulfide with oxygen. You can see we got our different bonds on here. We got 2 HS, HS, and 3 double oxygen bond, and we've got water, we've got oxygen hydrogen bonds, etc. So in this reaction, the energy release forming new bonds is, so it's going to give some energy. The energy release forming new bonds is 1,034 kilojoules per mole, greater than energy needed to break these 16 bonds. Calculate the bond energy. So calculate the bond energy X for the bond. So we're trying to find out this missing bond here. So what is the bond energy for a single bond of SO? So as with all these bond energy calculations, we do have to work out what bonds are broken. So at the beginning of the reaction here, these are our bonds broken. So we would it out first. So it's better if you label it, so you won't get confused. Bonds broken. So my bonds broken are going to be my 2HS and H, and my 3 O double bond oxygens. And we'll work across each one. Now, if I look here, I've got 1 bond of HS, 2 bond of HS. There's a ×2 here. That means there's 4. I'll show you again. That's 1. So got 1 bond here. That's 1. That's 2. There's 2 in front, so it's 2 times 2. So I have 4 SH in total. SH is 364. So my first calculation is 4 times 364. The next one is more simpler. So I've got 3 from the oxygens. So that's going to be 3 times 498. I then work this out and then do a total. So the total of the answers of both these is 2,950. So that's my total of my bonds broken. That's the first part. So bonds broken is this part of the equation. This is bonds broken. Now my bonds formed. The bonds formed at the end here. Now bear in mind, I don't know SO, but I do know the overall at the end. So my bonds formed. So the energy from bond forming, I need to know what I've got here. So my total here. So 2,950. I have to add on the extra to get the rest of the energy, plus 1,034, which will give me 3,984. And now I have my bonds formed. Now, I've got all my energy. I know what the bonds formed at the end is. I just don't know what SO is. So to do that, I have to look here. So as same as before, I've got one SO bond here, another SO bond here. It's 2. There's 2 in front of it. So I don't have 2 SO bonds. I have 4 SOO bonds. Now, because we don't know what SO is, we're going to refer to SO as X. So it's going to be 4X, just like we do in maths. So it's going to be 4X plus, now, because we want to work out what X is, we need to use the water to work out our missing numbers. So same again, I don't just have 2 HOs, I've got 2 versions, got 1 here, got 2 here, times it by 2, I have 4 H2O bonds. And this would be 4 times 464 bracket, and it will give me a total of 3984. So our next step is to now try and remove everything, make X the subject ultimately. So 4X will then equal 3984. Now, because there's a plus here, I'm going to take away the total of 464. The answer for that is actually 1856. So that's actually the answer for this bit here. So 3984 minus 1856 from above will then leave me with 2128. Now, so now I'm left with 4x equals 2128. If I want x, I divide by 4. Because of together, that means it's multiply. So 2128, then divide by 4, means x equals 532 kilojoules per mole. Oh, sorry. I'll just scroll down more. I didn't realise. Let's see. That's the full working out. I'll just run for that again. So what are they? So I've got our bonds formed. I've got the energy for bonds broken. I've also added in the energy for forming new bonds on top from my bonds formed. Then I have the total energy of all the bonds. And then what I did was I then used that to subtract the water, the bonds from water, away from it to then make X a subject. And I did that by subtracting it and then dividing by 4, see here, and I got 532. And that is the end of the energy changes videos. Thank you, everybody.